Hello everyone. In this video, I'm going to go over the topics covered during week 7 of the course, L7-1, lists, sets, and linked lists, and L7-2, stacks, queues, and Deques. Let's take a look at L7-1, lists, sets, and linked lists. Learner objectives for this lesson include reviewing lists, sets, and linked lists. These are topics that were likely covered in your previous computer science courses, and then performing algorithm analysis of the operations associated with lists, sets, and linked lists. So let's talk a little bit about linear versus nonlinear data structures. So stacks, queues, Deques, and lists are examples of data collections whose items are ordered depending on how they are added or removed. Once an item is added, it stays in that position relative to the other elements that came before and after this. So these structures are often called linear data structures, and you can think of them as having two ends. So this might be the left or the right, or perhaps the front and the rear, or maybe even the top and the bottom. Left and right, you might think of a list, the left side of the list, the right side of the list, or front and rear. Same with a list or even with a queue. You could think about top and bottom in terms of a stack as another example. So what distinguishes one linear structure from another is the way in which items are added and removed, in particular the location where the additions and removals occur. So a structure might only allow items to be inserted at one end. Some structures might allow items to be removed from either end, as is the case with a deck, for example. So sets, dictionaries, trees, and graphs are examples of nonlinear data structures. For nonlinear structures, the relationship of adjacency is not maintained between the items. So we're going to go over list, sets, and linked lists in this lesson. A list is a sequence of items. We've been working with lists for quite some time in the class so far. In a Python list, the data can be any type, but we know this isn't necessarily the case with some other implementations of lists, such as a ND array from NumPy or a series from Pandas. So here are common list operations and their time complexity. Now, these time complexities are based on the implementation specifically for Python. A general list abstract data type might have different time complexities depending on the underlying implementation. A set is an unordered collection with no duplicate elements. Basic uses include membership testing and eliminating duplicate entries. We will see an example of sets later in the course when we learn about graphs and common graph algorithms. There are common operations associated with the set abstract data type, including union, intersection, difference, and symmetric difference. Curly braces or the set function can be used to create sets. So a set is built into Python as a data type. We are going to just look at a set from the perspective of the data type built into Python, but a great exercise would be to implement your own set abstract data type with certain operations such as add, remove, stir, iterator, contains, etc. So here's an example here with a set of state abbreviations and a set of capitals. So if we run this code and we print out states and capitals, we see the curly braces denoting this is a set. We can also build a set from a string where we will have unique characters in that string stored in our set. So for example, the word hello only has unique letters L, H, E, and O. So the main thing to remember about sets is there are no duplicate entries. So when you think about how you might implement add operation for a set, you would check to make sure that the new item is not already in the set in order to add it. And if it is in the set, then perhaps update the element. Down here I have a few examples of testing the length of the word hello and the length of the word set. This is false because there are 4 items in the hello set, and there are 5 letters in the hello string. Printing out the type, we see that states is a set, and we see that ID is an element in the state set, but MT, Montana, is not. Here are common operations associated with sets. Union returns a set with elements from the set and all others. So this is the way to essentially add two sets together. Intersection, return a new set with elements common to the set and all others. So this is a way to add two or more sets together only with common items. Difference returns a new set with elements in the set that are not in the others. So a way to subtract the items from one set from another. The symmetric difference returns a new set with elements in either set but not in both. So this would be a way to identify the inverse, essentially, of what is common between two sets. Subset, test whether every element in the set is in another. A proper set would be a set that is strictly a subset and not equal to the set, meaning not all items in the subset are in the original set. Superset, test whether every element in the other is in the set, and test whether the set is a proper superset of the other. Here are some examples of the common operations. I will run this, but I'm not going to go through all of these examples. This would be great to walk through step by step. For example, the union of LHEO and LHPE would be no duplicates, but a combination of all of these letters. So we see LHEO from the first set, and we also see P from the second set. And then the intersection would be only those that are common. So O and P are not in both sets, so we only have HEL as the intersection. Moving on to linked lists. A linked list is a list of linked items with no requirement that the items are stored contiguously in memory. If we know the location of the first item in memory, also called the head of the list, the first item will tell us where the second item is because they are linked, and so on and so forth. So all we need to do is store a reference to the first item in the list. This is typically called the head or the head reference. And from the head reference, we can access all items in the list by traversing through the list following the links. Now, there are many different implementations of linked lists. Many of these are covered in introductory computer science classes, such as singly linked and circular linked, but we can also have doubly linked, circular, and also ordered, for example. Depending on the needs of the linked list and the problem, different implementations may be deployed. So I'm not going to go over the details of the implementation of linked lists in Python because I know that you have familiarity with linked lists from the prerequisite courses, but I do recommend going through this code here and testing out how the linked list code works with an unordered linked list implementation, and later in the document, an ordered linked list implementation. For an ordered linked list, we restrict that when we add items to the linked list, they must be added in order. So at any given point in time, the list is always in sorted order. With an unordered linked list, we could write a sort routine to sort it at a time later should we need it to be sorted. So the trade-off here is where are you going to spend your time to perform a sorting routine upon insertion or later when needed, if needed. Here are the time complexities for common linked list operations. I have some notes here that describe that different implementations can result in different time complexities. So let's just take a look at add item. This is constant time complexity because if we always add to the front of an ordered list, we just need to update our head link and our new item link. If this is going to be a circular linked list or a doubly linked list, then more links will need to be updated. If this is an ordered linked list, then the time complexity is big O of n because we have to traverse the nodes in order to find the correct location to insert the new node. If we want to write an append, which would add an item to the end of the list, With a singly linked list, this would be linear time complexity because we have to traverse to get to the end of the list. However, with a different implementation, such as a doubly linked list, or simply by maintaining a tail pointer to the last item in the list, this can be constant time complexity. It's very similar to adding to the front of the list by updating a head pointer, but this time with a tail pointer. Or looking at the head node's previous pointer. And I will let you take some time to look through the time complexities. And as you're looking at these time complexities, run through the algorithm in your head so that you are aware of how would this be implemented and why is the time complexity as is. So for example, is empty is constant because you only need to check the head reference or the head pointer in order to know if there are any items in the list. I have some practice problems here that I recommend working through to review your list, linked list, and set skills. And like I said, when implementing any of these algorithms, be thinking about the time complexity and the efficiency for these algorithms and asking yourself questions such as the notes I have here. Does the implementation perhaps change the time complexity? And how can we make one implementation more efficient than another? So let's move on to L7-2, which will have a similar flavor to L7-1, where we are revisiting some of the data structures learned in previous courses, looking at their time complexities, and also covering possibly a new topic, a Deque, which is a double-ended queue. So learner objectives for this lesson: review stacks and queues, learn about Deques, and perform algorithm analysis for these data structures. So let's start with a stack. A stack is an ordered collection of items where the addition of new items and the removal of existing items always take place at the same end. We would typically call this end of the queue, of the stack, top, and the bottom would be called the base or the bottom of the queue, the stack, So there's a nice structure here, or a nice diagram here, that shows a stack. So down here would be the bottom or the base, and up here would be the top, and we only add items to the top of the stack and remove items from the top of the stack. This is commonly called a LIFO, last in, first out data structure, because the last item in will be the first item out. Now, the main operations to add and remove items to a stack are not called add and remove. They're typically called push and pop. We would push an item onto the stack, and when we want to remove an item, we would pop it off of the stack. Here is a stack implementation with a list. This is a standard Python list that supports adding items to one end and only popping items from one end. So for example, push, we're going to append an item to the end of the stack. So you can think about the beginning of a list, item position 0 being the bottom, and the last position, -1, or length n-1, being the top of our stack. And for popping items off the stack, there's actually a list method called pop, which we have seen previously in the course, that will remove the last item from the list and return it. A few other operations commonly associated with stacks include peek. So this will just look at the top item on the stack. It will not remove it, but will return it. So this is a way you can gain some insight as to what is the top item on the stack. So here we're just going to look at the item in the last position of the list. And of course, size, how many items are on the stack, and is empty, is this stack empty or not? Here's some example code here that walks through making a stack, pushing some items onto the stack, printing out the stack, and then popping an item and printing out again. And the output for printing is coming from this very simple stir method here, showing the bottom and the top of the stack. So since apples was the last item to be pushed onto the stack, it is towards the top. Once we remove an item by popping, then we pop apples, and now milk is the top of the stack. So the time complexities for these stack operations are as you would expect. These are actually based on the underlying data structure of a Python list. To push an item is constant time complexity. To pop and peek are constant time complexity. To figure out the size is actually linear time n, because we have to traverse through the list. But we could implement this such that it was constant by keeping track of the number of items every time we push and the number of items every time we pop with a simple attribute counter. And is empty is constant time complexity. We only have to compare if there is an item in the list or not. Now let's talk about queues. A queue is an ordered collection of items where the addition of new items happens at one end, called the rear of the queue, and the removal of existing items occurs at the other end of the queue, commonly called the front. As an element enters the queue, it starts at the rear and makes its way toward the front, waiting until the time when it is the next item to be removed. So this kind of structure is typically called FIFO, first in, first out. The first item added to the queue will be the first item that is removed from the queue. This also makes sense in terms of perhaps a queue, in terms of maybe a line at a cash register or at a store or at a traffic light. The first one to arrive there is the first one served, or the first one who gets to leave. So here's a nice diagram showing a queue. Here's the back of our queue, and here is the front of our queue. We add items to the back. This operation is commonly called enqueuing an item, and we remove items from the front. This operation is commonly called dequeuing an item. Here is a queue implementation with a list. You will see some parallelism between the queue implementation and the stack implementation using a list. Let's take a look at some of the common operations, such as enqueue. In this case, we're calling the item at the 0th position to be the rear of the queue. So item position 0 is the rear of the queue, and item at position n is the front of the queue. So we enqueue at position 0, and we dequeue at the last position, which we could just pop an item off of the list, just like we would do with the pop method of our stack. Here is an example here, building a queue of eggs, milk, and apples, printing out the queue, dequeuing the item at the front, and printing out groceries again. So this is going to be the result of a simple stir method associated with the queue class. So we add eggs, milk, and apples. So since it's a FIFO structure, eggs is the first in, it will be the first out. After we remove eggs, milk goes to the front of the queue because it was added before apples. Here are the time complexities for common queue operations. So enqueue and dequeue. Enqueue and dequeue are constant based on their implementation in Python lists. Size, we have to traverse through the queue to find out how many items are there. Or like I said, for a stack, we could keep track of this with a counter and just change some code in our enqueue and dequeue methods. And ins empty, time complexity, big O of 1. So the last structure we're going to talk about in this lesson is a deque. A deque is also known as a double-ended queue. It is an ordered collection of items similar to a queue. Unlike a queue, there is no restriction on which end you add to and which end you remove from. It has two ends, a front and a rear, and the items remain positioned in the collection, but there's no restriction on whether the front is for enqueuing or dequeuing, or the rear is for enqueuing or dequeuing. So this hybrid linear structure provides all the capabilities of stacks and queues in a single data structure. In fact, you can think of a Python list as a deque because we can just choose in our implementation whether we're going to restrict adding or removing from certain ends. So here's a diagram that shows what a deque looks like. So here's the rear, here's the front, or here's the front and here's the rear. You can NQ and DQ from either end. This is up to you, the programmer, to perhaps put restrictions on this. So here's a Deques implementation with a list. Really, it's just providing kind of a interface into the interface already provided by a Python list. So we'll have an add front and an add rear and a remove front and a remove rear. So in this case, the front of the Deques is considered to be the last position in our list. So when we add front, we append. When we remove front, we pop. So when we add rear, we insert at position 0, and when we remove rear, we pop at position 0. Here is an example going through making a Deques, adding to the front eggs and milk, and printing out groceries. So we add to the front eggs first and then milk. Eggs is pushed to the rear. And then if we add rear apples, then apples comes in on the other side of eggs. We remove rear, then we remove apples. We remove front, then we're going to remove milk, and that just leaves us with eggs. So you can see we can add to either end and we can remove to either end. Here are the time complexities for common Deques operations. Our adding and removing is constant depending on your implementation, but you could think about not using a Python list and instead using a linked list with a head and a tail pointer, and then you can easily add from the front and rear and remove from the front and rear without traversing through the list. Size, linear, but like I said earlier, for the stack and for the queue, we could get this to be constant time complexity, and is empty constant as well. Here are some practice problems to work through in order to fully understand and flesh out your knowledge of stacks, queues, and Deques. And with that, this wraps up the topics covered in the lessons for week 7 of the course.